Hey everyone! Today we're going to try and hack the impossible. We're digging into a problem-solving strategy that, even though it has a technical name, backtracking, is actually one of the most intuitive tools you can have. So forget about dry algorithms for a minute. Think of this as a mental model for cracking puzzles that seem to have just endless possibilities.
Okay, so let's start with a big question. When you've got a computer facing a puzzle with millions or heck, even billions of potential answers, how does it actually find the right one? How do you tell it to find a needle in a cosmic haystack without it taking like a million years?
To really get a grip on this clever approach, we need a test case. And we're going to use a classic computer science puzzle that is just perfectly designed for this kind of challenge. It's called the n queens problem. The rules here are pretty simple. The goal is to place n queens on an n by n chessboard. So let's just imagine 8 queens on a regular 8 by 8 board. Now, here's the catch. No 2 queens are allowed to attack each other. That means no 2 queens can be on the same row, the same column, or even on the same diagonal. Sounds easy, right? Well, as you're about to see, it's a surprisingly tricky puzzle to solve efficiently. And this is where the scale of the problem just absolutely explodes. If you tried to check every single possible combination for an 8 by 8 board, you'd be looking at over 4 times billion possibilities. And hidden inside all that noise are just 92 correct answers. So trying to brute force it isn't just slow, it's computationally insane. We definitely need a smarter way. And that smarter way is what I like to call the oops, go back strategy. Its official name is backtracking, and it's pretty much the hero of our story today. You know, this quote really nails it. Instead of building a whole solution and then checking if it works, you check at every single step. You're constantly asking yourself, is this path I'm on still good? Does it have a chance? And the very moment the answer is nope, you just stop. You don't waste another second going down a path that's already broken. The absolute best analogy for backtracking is a maze, right? You pick a path and you start walking. When you hit a dead end, a brick wall, you don't just give up and sit there. You simply turn around, walk back to the last place you had a choice, and you try a different path. It's really that simple. So it all boils down to this little 3-step loop. First, you make a choice, you move forward. Second, you check if it's feasible. Did you just hit a wall? And third, if that path is blocked, you backtrack. You just go back and try another option. You just keep doing that over and over again until you find a way out. Now let's see how this maze idea looks from a more formal, computer science point of view. Because all of these choices and all these paths, you can actually visualize them as a giant decision tree. This image shows it perfectly. In computer science, this is called a state space tree. Every possible move you make creates a new branch. Now, trying to explore this entire tree would be impossible. Backtracking is the smart way to navigate it. The moment we realize a branch leads to a dead end, we prune it. We just snip it right off and ignore that entire section of possibilities, which saves a massive amount of work. And just to get the lingo down, the path we're currently on is called an E-node, or an expanding node. Think of it as a live path, one with potential. But as soon as we hit that wall, that path becomes a dead node. It's a goner. And by marking it as dead, we make sure we never waste our time going down that same wrong path again. Okay, theory is great, but let's actually see this thing in action. We're going to solve the 4 queens problem, so a smaller 4x4 board. It's way easier to visualize, but the backtracking logic is exactly the same. All right, here we go. First choice, we'll place queen 1 in the top left corner. That's row 1, column 1. So far, so good. No other queens are on the board, so there are no conflicts. This is a promising start. Our path is live. Okay, next up, queen 2 in the second row. We have to check our options. Column 1? Nope, that's directly blocked. Column 2 is in a diagonal attack path, but column 3 looks totally safe. So we make our choice and we place queen 2 right there. Still looking good. Now for queen 3 in the third row. Let's check the columns one by one. Column 1, blocked by queen 1. Column 2, blocked by queen 1's diagonal. Column 3, blocked by queen 2. And column 4 is blocked by queen 2's diagonal. Uh-oh, there's nowhere safe to place our third queen. We've hit a wall. This path is officially a dead end. So what now? Well, this is the key moment. We execute the core mechanic of the whole thing. We backtrack. We undo our last move, and we go back to the previous decision to try something else. Our last decision was for queen 3, but there were no other options there. So we have to go back one step further, all the way to queen 2. Remember, we put it in column 3. So we pick it up, and we try its next available spot, which is column 4. And just like that, we have a new, unexplored path to follow. And would you look at that? From this new position for Queen 2, a solution just opens right up. We can now place Queen 3 in a safe spot over in column 2. And with that move made, Queen 4 finds a home in column 3. And that's it. Every queen is placed, no one's under attack, we've found a solution. That is the power of backtracking. Now, this isn't just about solving chess puzzles. Backtracking is a really fundamental technique that shows up everywhere, solving all sorts of complex, real-world problems. I mean, it's used in financial analysis to find subsets of numbers that add up to a specific target. It's used for scheduling and figuring out how to assign resources through something called graph coloring. It's even used in logistics to find the most efficient routes for delivery trucks. And yup, pretty much every Sudoku solver you've ever played with is powered by a backtracking algorithm, just trying and backtracking until it finds the solution. So just remember this, backtracking is your go-to tool for any problem with a huge number of possibilities, but a clear set of rules. It lets a computer systematically explore all the options while intelligently just abandoning the paths that are guaranteed to fail. It saves an incredible amount of time. And that leaves us with one last thought. This simple idea of trying a path, checking for dead ends, and being willing to go back is just incredibly powerful. It really makes you wonder, what other impossible problems could we solve, not with more computing power, but just by knowing when it's time to turn back and try a different path? Thanks for exploring this with me.